Okay guys, so today we're going to talk, or we're going to go through an introduction of Root Locus Method. The whole idea of this video is to get you started on the concept of Root Locus Method so we can go into a lecture and start working examples and start working problems as soon as possible. This will make the process a little bit easier and simpler for all of us. So let's start with the Root Locus Method. Basically, so far we have seen that the location of the roots of the closed loop system define if the system is stable or not. So we want to know if the system is stable and what type of transient performance we're going to do or we're going to have. So what we're going to do, or we're going to talk about, is adjusting one or more of the parameters of our system in order to place our locations on a suitable place. So the roots on this characteristic function can be placed on the S-plane, and based on that we're going to be able to figure out how the system is going to behave, if it's going to be stable, unstable, if it's going to be overdamp, underdamp, or critical damp. So this is very important. Root Locus Method will allow us to find how the roots move around the S-plane when these parameters are changed. This method was invented by Evans in 1948. Okay, it's a graphical method that allows us to see how the roots move, and it's really useful when we use it in conjunction with Root-Hurwitz criteria. So if we look at the figure right here on this PowerPoint, hold on, okay. So if we look at the figure in there, what we are looking at in here, oh, not the correct one, this one. If we look here, we have couple of poles, and the circles are zeros. So we can see when in this root locus, when we change the parameter of this system, basically this root is following this green line, and it's going from this position, and as we change the parameter, the root goes and moves, crosses the imaginary plane and keeps moving up. The same happens for this root. This root is moving in this direction. These two roots move together. Basically, they collide in the middle. One starts shooting up, and the other one starts shooting down. So the whole idea of this method is we're going to know how to create these plots by hand. Eventually, I'll show you how to use MATLAB to create the plots. But for now, we're going to assume that we don't have a computer, and we're going to do it by hand. So let's continue with the process. So let's assume we have a closed loop transfer function. So our closed loop transfer function looks like this thing, okay, where we have a polynomial on the top and a polynomial at the bottom. If we grab the polynomial at the denominator, okay, and make it equal to 0, basically we're going to have our characteristic function. And the characteristic function will allow us to find out the modes of our response, if the response is going to be overdamp, underdamp, or critical damped. So consider a system like this. So we have a system, and we have here our basically the input R of S and the output Y of S. Okay, here we have a constant K and the system parameter G of S. So the characteristic equation of our system, basically if we use Mason's rule, it is going to be equal to, if you remember, basically this is going to be, oh, I don't know why it made that. Let me erase it. So we know that these basically will become our delta S, and this is going to be our characteristic function. So we grab delta S, make it equal to 0, and we have our characteristic function. Now we want our characteristic function in this form in order to use the Root Locus method. Okay? So make sure that our characteristic function works or is looking in that specific way. Now, on this characteristic function, we have been working so far with the S from the Laplace transform. Okay, so S, so you know it, S can be represented in the Laplace domain, or if we decide to change S to j omega, we make a change of variables, then we will have the Fourier transform, or basically the Fourier representation of our transfer function. For now, let's just keep it as S for our calculations. So if we grab our characteristic function, okay, and we solve for kg of s, basically we can say that kg of s will be equal to 1. this equation will be very important at figuring out all our parameters on the equation. This is going to define some of the constraints that we're going to use on our root locus method. So here we have our equation, and I forgot a negative when I solve it in here, so it's a -1. So we have our equation kg of s equals to -1. Okay. Now, because kg of s it's a transfer function in the Laplace domain, that means it has a real and imaginary part. So that means if it's real and imaginary, it has a real and imaginary part. We can put it in terms of phasors. So we can have the magnitude and the angle. Now, something interesting from here. If we look at the number -1 and we transform that number -1 into a phasor, this is going to be equal to 1 with an angle of -180 degrees or 180 degrees. It doesn't make a difference. So that means that our magnitude k, the magnitude of k times g of s, should be always equals to 1. This is really interesting because it doesn't matter the value of s that we pick, that magnitude should be always equal to 1. So that means there's going to be a limited number or a limited range of values of s that will satisfy this condition. The other one is that the angle of kg of s should be equal to either 180 degrees minus 180 degrees or any multiple of 180 degrees. So the same situation happens here. It doesn't matter, or it do matter, but there's going to be a limited number of parameters or a limited number of values of s that will satisfy that condition. Okay, so basically from here we get the concept of root locus. The root locus is the path of the roots of the characteristic equation traced out in the s-plane as a system parameter varies from 0 to infinity. So what is going to happen on the root locus, we're going to see all the values of s that are going to be satisfying this condition as we change the constant or the system parameter k. Okay, so let's move forward and keep looking at this. So let's assume we have a system like this, or we have our same system. So it's our parameter k, okay, and then we have 1 over s times s plus 2. So when we find out our characteristic function, delta of s will be equal to 1 plus kg of s. So we write everything in terms of our values, and then we have basically our characteristic equation. So now from here, we can look at this, and here it's our characteristic equation placed as a polynomial. So from here we can see this is a second order polynomial. So if it's a second order polynomial, that means that we can use, we can find out the roots of this polynomial fairly easy. So let's look at that really quick. So we know that these conditions should be satisfied. The magnitude of our the magnitude of k times gs should be equal to 1, and the angle of k times gs should be always equal to 180 degrees. So that means the roots that we are going to find from that second order polynomial should satisfy those conditions. So if we substitute s1 here and s1 here, should satisfy that condition. If we substitute s2 in here and s2 in here, they should satisfy that condition. So if we work that problem, let's say if k is equal to 0 first, okay, the roots that we find are s1 and s2 being equal to -2 and 0. So those are the roots for k equals 0. Now what will happen if we increase k? If we go from k0 and we start increasing it slowly, what is going to happen, this root at -2 will start moving in this direction, will start moving to the right. At the same time, this root at 0 will start moving to the left. Then what's going to happen? At some point in time, they will kind of collide, and one of the roots will jump vertically, and the other root will jump vertically, but now it's going to go down. Okay? Now, because that's the situation, still the condition about the magnitude and the angle should be equal to 1. Well, the magnitude should be equal to 1, the angle should be equal to 0. Sorry, to 180 degrees. So let me show you something. So if you think about vectors, okay, and you think about the vectors that are required to go from one root to the other root, okay, so the vector going from from this root, the root at 0 to a root 2, it's a vector that has an angle of how much? 180 degrees. And the vector that goes from 0 to 0, it's an angle of 0 degrees. So you can see the sum of the angles make up 180 degrees. Okay? There are different ways to look at this. We're going to see it later when we start looking into how to calculate the angles. But for now, it is important that you understand that this characteristic equation should satisfy those conditions all the time. So basically those are the conditions that need to be satisfied. So let's test a value, or let's test one value on this blue line. These blue lines represent how the roots are going to be moving. So if we pick a value of s equals to -1 plus j2, basically we're looking at a value of -1 and j2. So that will be, so this is -1 and j2 is going to be somewhere in here, let's say. Okay, so we pick that value and substitute that value into our equation. Okay, so we look at the angle. Okay, so we look at the angle of this on this equation. So if we calculate the angle, we're going to find out that the angle of this phasor, or the angle of this thing, is going to be equal to 180 degrees. So if we said, okay, basically this is going to be the angle of minus s, and well, minus the angle of s minus the angle of s plus 2. Okay, we've calculated the arctangent of that, and we basically get an angle of minus 180 degrees. The question is how we got these expressions. So let's look at it really quick. So let me erase this ink, and let's look at the equation for the angle. So this is my polynomial. Okay, so we're looking at the angle of this thing. So it's going to be k times s plus 2. Okay, so we have this, basically the angle of this thing should be equal to 180 degrees. Okay, so if we said, let's just pick a value of k, it doesn't matter really which value, because we're looking at the angles. So if k is a constant, it's a constant number, so it will have an angle of 0. So we'll have an angle of 0 divided by the angle of s, and because these two are multiplying, basically what's going to happen with the angles when we multiply phasors, they're going to be added together. Okay, so it's going to be plus the angle of s plus 2. So we do it in this way, and basically we say this angle of 0 minus the angles in here, so that's where we get this expression. Then we substitute s, or so we substitute the values here, and we substitute the values here. Okay, so when we have here minus the angle of -1 plus j2, this is basically the arctangent of 2 over -1. Okay, and then on the other one we have here the angle of -1 plus j2 plus 2. So this is equal to 1 plus j2. So basically this is going to be the arctangent of 2 over 1. So this one corresponds to the value here, and this one corresponds to the value here. Okay, so now when we calculate the numbers, we plug in the values into the calculator. What we obtain is the angle of minus 180 degrees. So we know this is satisfied. This is basically working the way we expected. So let's go and talk really quick about the procedure. So the first thing that we're going to need to do when we are working Root Locus method, we're going to grab our characteristic equation or our delta S and put it in this form. 1 plus a polynomial, or basically this equation that will have on the top the zeros and at the bottom the poles. Okay? Then the next thing we do, we identify the poles and the zeros. We identify the poles, basically the values of this polynomial, and the zeros, the values of this polynomial. Once we identify them, we draw them on the S-plane. We create basically an X for a pole and a 0 for a 0. So let's look at this example. So let's say this is our characteristic function. Okay, you can see the parameter k in there. So we work our characteristic function and we put it in this form. Now we basically using algebra, regular algebra, we're gonna write it in a form that we can have a 1 plus something. So one way to do it, it is we grab basically what is the constant, or this part in here, and divide everything by s squared plus 2s minus 3. So this will give us a 1 in here. I don't know why it's doing that. We have a 1 in here, and then we divide everything by s squared plus 2s minus 3. So we identify the poles and the zeros. So the 0 is located at 2, and the pole is they're going to be located at 1 and minus 3. So that's basically what we have in here. Okay, so we have 1 0 and 2 poles. So next thing is we need to draw them on the S-plane. Right now I don't have any grid paper in here, so I'll just make a really quick sketch of how this thing is going to look like. So we have one pole at minus 3, another pole at 1, okay, and another pole in a 0 located at 2. Got it? So this is the first 3 steps. So let's go back and summarize the 3 steps. So we write our equation in that specific form, we identify the poles and the zeros, and then we draw them on the S-plane. So that's exactly what we did in here. So now let's move into the 4th step. It's what we call finding the root locus segment. Okay? What is going to happen, think about the center of our axis is going to be the center, okay, or basically the reference point. So what is going to happen, our poles will try to move away from the center of our axis, while the zeros are going to try to move into the center of our axis. But they are not alone. They are going to interact one to each other. Okay? So what's going to happen is the root locus on a real axis always lies on a section of the real axis to the left of an odd number of poles and zero. That sounded really weird, right? So let me show you what I mean. Let's just make sure. So we need to draw the root locus segment. So let me just give you the same drawing here. So here's my vertical axis, or my j omega axis. We have one root, or one pole at 1, a 0 at 2, okay, and another pole at minus 3. So what we're going to look at, we're going to count the number of roots. In every odd root, we're going to draw a segment to the left of that specific pole or 0. So this is basically root 1, root 2, and root 3. It is pretty obvious which ones are the odd. This one is the odd, and this one is the odd. Okay, so the segment will be the segment that is located at the left of our pole. So that means the segment is located to the left, and it goes all the way up to infinity. Now the segment here goes to the left of this 0, so it goes in this direction. But it's not going to go up to infinity, or it's not going to touch the center of our axis. It will actually stop at our next pole, or at our next 0. Okay? So these are going to be our 2 segments. Got it? So then the next thing we need to do, let's check just the angle criterion. So we have, if we look at our equation in this way, let me just clear it really quick so we can work with these expressions. So when we look at this expression, basically we're looking for the angles of this thing. Okay, so we're basically looking at the angle of the expression s minus 2 over the angle of s minus 1 plus the angle of s plus 3. So when we simplify everything, this whole thing is going to look like the angle of s plus 2 minus the angle of s plus 1, s minus 1. Let me delete that because it's going to get confusing if I don't do it. S minus 1 minus the angle of s plus 3. Okay, so that's pretty much what we have in here. So the angle of s minus 2 minus the angle of s minus 1 minus the angle of s plus 3. Let's check the angle criteria. So we know that the segment it's located from minus 3 all the way up to infinity. So let's pick a value of minus 4. And we're going to pick another value. We're going to pick another value at minus 1.5. Okay? So minus 1.5 should be in here. Minus 1.5 should not work. There's something weird in here. Okay, that should be a typo. That will be a typo. Okay, forget about this minus 1.5, but let's check the minus 4. So when we substitute the minus 4 here, we're going to have minus 4, and minus 4 in here. So we have minus 4 plus minus 2. This will give us a minus 6. Okay, this will give us a minus 5. And this one will give us a minus, what's going to be minus 1. So when we look at this, these are negative numbers. So this one will have an angle of 180 degrees, 180 degrees, 180 degrees. So we have 180 minus 180 minus 180 equals to minus 180. Got it? So now, let's keep moving forward. How about the magnitude criteria? We know that the magnitude of this thing should be equal to 1. Okay, so that means the magnitude of this thing should be equal to 1 over k. So if we substitute our s equals to minus 4, okay, basically we're checking if I want to pick a value of minus 4 that is located on a segment, then what is going to happen, I will find out, or I will be able to find my value of k, allowing me to figure out which value of k will make this root to move from minus 3 into minus 4. Got it? And I still have a problem with that. Oh, there's the problem. It is not minus 1.5. So let's work it out. So it's a plus 1.5. So if it's a plus 1.5, this will be equal to what? It's going to be, so it's going to be minus 0.5, and then plus 0.5, and then plus 0.5, sorry, yeah, and then it's going to be so this is going to be plus 4.5. So this one has an angle of 180 degrees, an angle of 0, and an angle of 0, giving us the criteria. So we basically pick a value of plus 1.5. It is not this value, but actually a value right in here of 1.5. So that validates our result. So when we look at the criteria, okay, the value of k that will generate that root to move into the 1.5 value will be equal to a k of 4.5. Okay, these root locus segment, or these little segments that we found on our axis, is what we call the separate loci. Okay, loci. Sorry, it's loci. So the number of separate loci is basically equal to the number of poles that we have in our system. So in this case, we had 2 poles. Okay, we have the pole at -3 and the pole at 1. So that means we have 2 separate loci on our system. Okay, and these loci are typically symmetrical with respect to the horizontal real axis. Right now we didn't have any of those because all of them were located right on the real axis, but later we'll see how they are symmetrical with the axis. The next thing we'll learn is there's going to be something that will allow us to know how they're going to move when they move outside the real axis. And those are going to be the asymptotes and the asymptote centroids. Basically using the 2 equations that we have here, sigma and delta, or by calculating sigma and by calculating delta, we'll be able to find out where is the asymptote centroid. That's where all the asymptotes merge or touch. And then we're going to have the angle of the asymptotes that we have. The angle of the asymptotes will be equal to 2k plus 1 over n minus m times 180 degrees, where k will pick values from 0 to 1. Okay, and n and m represents the number of poles, n represents the number of poles, m represents the number of zeros. How I know that? If we look at the equation here and here, this is for the poles and this is for the zeros. Okay, and then basically the centroid will be equal to the summation of all the negative of the poles minus the summation of the negative of the zeros divided by the difference between the poles and the zeros. One example, here we have this example in here. So we have the summation of the negative of the poles. So this pole is going to be what? Well, it's not actually that much of a negative pole. So this pole is going to be 1 and minus 3. Okay, and the zeros will be located at 2. Okay, so what's first? How many poles we have? So we have n equals 2 and m equals 1. So we have 2 poles and 1 zero. Okay, then we make the summation. Okay, so the sum of the poles minus the sum of the zeros. So it's going to be plus 1 plus minus 3 minus plus 2 over 2 minus 1. This gives us a centroid of minus 4. Okay, then we use our equation 2k plus 1 over n minus m. n minus m is equal to 1. And 2k plus 1 times 180 degrees. Now in here, what we're going to do, we're going to use all the values of k that will allow us to go around the circle just once. Or basically, we're not going to go over 360 degrees. So when k is equal to 0, we have 1 over 1 times 180 degrees, give us 180 degrees. If we go with k equals 1, what's going to happen? This is going to be 2 plus 1 over 1. That's basically going to be equal to 3. So 3 times 180 degrees, that will give us, basically, we'll go 1 full rotation and around a little bit. So then we have exceeded 360 degrees. Then we're not allowed to use k equals 1. So the only parameter of k that we're going to look at is for k equals 0. Let's look at another example. So how many poles we have here? We have a pole at 0, at minus 2, okay, and then another one at, it is going to be what, minus 4, and this one is a repeated pole because it's square. And then how many zeros we have? We have a 0 at minus 1. So we apply our equation. So it's going to be 0 plus minus 2 plus minus 4 plus minus 4 plus, here's the 0, I read it at the very beginning, minus our 0, so it's going to be minus minus 1. divided by the number of poles minus the number of zeros, so it's going to be 4 minus 1, and this gives us a centroid of minus 3. Then the next thing we do, we calculate the angles. So for k equals 0, we have 60 degrees. For k equals 1, we have 180 degrees. And for k equals 2, we have 300 degrees. There's no way we can go further than that. So we're going to say that's all that we're going to use. Case 0, 1, and 2. Then what's going to happen? Let's look at the S-plane. So here we have our pole at 0, pole at minus 2, and our two poles at minus 4. And then we have our loci or loci. So we have this is basically 1. So we have a segment to the left. Then we have 1, 2, this is 3, a segment to the left. And there's 4 and 5 goes to the left. Okay, so that will create basically all our locis in here. So you can see the blue lines represent our locis. And then we look at the centroid. Where is that centroid located? The centroid is located at minus 3. So it's going to be right in here at minus 3. And then from the centroid, we're going to draw our asymptotes. Those asymptotes will follow the angles of 180 degrees, 60 degrees, 180 degrees, and 300 degrees. So what is going to happen, one of these poles is going to move in this direction, the other pole will move in this direction. They're going to collide, and they're going to follow, one of them is going to follow the asymptote, the other one is going to follow the other asymptote, while this pole, it's basically merged, or it basically falls into the 0, and the remaining pole is going to move out to infinity. So what we're going to see is basically the drawing that we have on the right. You can see the pole moving to the right, going all the way to infinity, then one pole moving in, the other pole moving in, then they collide, and they follow the asymptotes after they collide. And then the other pole is drawn into the 0. Okay? Then from here we can find out steps 6, 7, and 6, 7, 8, and 9. I'm going to talk about this on lecture once we start covering this. So I'm going to stop here. I'll let you analyze this, digest this information. We're going to discuss it in the lecture. And if you have any questions, please ask me the next time we meet. So that's pretty much it, guys, for today. I'll see you in the next class. Bye-bye.